Okay, so in the last part of today's lecture, let's actually connect the orthogonality of Legendre polynomials with the concept of Legendre series. You will see some nice analogy with the sine and cosine functions. Basically, we're going to have Legendre series in general, even Legendre series, odd Legendre series, basically involving either even or odd polynomials. But let's talk about just the overall the Legendre series, right? So we have this orthogonality property on the interval -1 and 1. And by the way, at this point, you should essentially figure out how this will unfold in terms of solving the Sturm-Liouville problems. So if you have, for example, a Sturm-Liouville problem that simply is stated in terms of our Legendre equation, without any boundary conditions, besides continuity, of course. So basically, if your problem is in the form of a Sturm-Liouville problem and no other conditions are imposed on the, let's actually use big X here instead of, so big X of little x, because that's the typical notation sometimes on these problems. So if no other conditions is imposed on the dependent variable, except continuity, of course, because that's always an assumption, then the eigenvalues will simply be all the values of lambda which will produce the solution in the form of a polynomial, namely the Legendre polynomial. So basically all the lambdas in the form n times n plus 1 with n a natural number will be an eigenvalue, and Pn of x will be the eigenfunctions. And again, provided that the interval in question is -1 and 1. Let's not forget that. So because of the orthogonality, obviously, if you have a piecewise defined function, piecewise smooth function f of x, we can write it presumably in terms of a Legendre series involving these Legendre polynomials, a n Pn of x. How do you determine these coefficients? Well, this is the time when you use the orthogonality principle, right? So I mean, if I let's actually use a different index here. Let's say m0 to infinity am Pm of x, just so that I can provide a formula for an, right? So I mean, you have this summation, you multiply both sides by a fixed index n, you take the integral from -1 to 1, all the integrals will be 0 except the one when m is equal to n. So when I take the integrals on both sides from -1 to 1, this summation, all the terms will be 0 in this summation, and you are left with the integral from an on the outside, right? I mean the constant, and the integral from -1 to 1 Pn of x squared, because that's the only one that is not 0 when m is not equal to n, when n is equal to n, sorry. That's the only one when the integral is not 0. And so that gives you the coefficient an from this equation, right? So that integral is 2 over 2n plus 1, which means the coefficient, if you move this to the left, if you multiply both sides by 2n plus 1 over 2, this will be the formula for the coefficient of the Legendre series. And you should look at the formula sheet and you will see one version of the Legendre series given in this format for the coefficient. So I went a little bit faster on this one, and we have plenty of time to go over the other examples, but it's very important, just to reinforce what you learned in this class so far, to try to get a sensation of deja vu, because this is what we've done in different contexts: sine, cosine series, Bessel series, now the Legendre series. We use the orthogonality to be able to write a function in terms of this series. And the orthogonality is basically the property that gives me a quick way to determine these coefficients in that series representation. So this is what you have if you have, like I said, over the series over the interval -1 and 1 without any extra conditions imposed on it. Now, in some cases, we have extra boundary conditions, typically at 0. I mean, you'll see later why. I mean, when you take the portions of a sphere, right? Because remember, -1 and 1, it's tied up with cosine of theta between -1 and 1, which means theta is between -pi and pi. So, I mean, that's typically the case when you have a full sphere. But if you have a portion of a sphere, you have extra boundary conditions. For example, if I have a hemisphere, I need to have some boundary conditions on the flat bottom of the hemisphere. So then you have some other versions of the Legendre series when you have extra conditions and a different interval. So for example, let's say instead of this interval -1 and 1, suppose that the interval in question is 0, 1. And suppose that we have an extra condition, x of 0 equals 0. This is like a Dirichlet type of problem, or Dirichlet condition. Right? It could come from, for instance, maintaining the temperature 0 on one side. Well, the first thing to note is here that in the context of solving the Legendre equation, we know already that the solution of it, right, is going to be in the form of a series with those coefficients given by that order 2 recursion. When I say x of 0 equals 0, automatically that means a naught is equal to 0. Because when I plug in 0 for x, a naught equal to 0. And again, because of that recursion, that implies automatically all the even coefficients will be 0. And remember, when you solve an eigenvalue problem, a Sturm-Liouville problem, you're looking for non-zero solutions. So that means the only eigenvalues will be n times n plus 1 with n odd. Right? Because if n is even, those correspond to the even coefficients, which are 0 by default, because your starting point for the even part is equal to 0. One thing, I want to check something before we move along, so that I don't say, I want to make sure I don't say something on the, from the homework. Okay. All right, so only when n is odd, we have the eigenvalues for the problem, because only in that case we have non-zero solutions for the Sturm-Liouville problem. And because only the odd eigenvalues are taken into account, it's customary in that case to write the acceptable lambdas in terms of 2n plus 1, 2n plus 2. Remember, 2n plus 1 is the standard way of denoting an odd number. Furthermore, let's say the condition was x prime of 0 equals 0, which is a Newman condition. Well, if x prime of 0 equals 0, if I differentiate the solution, x prime of x will be a1 plus 2a2x plus dot dot dot. That means x prime of 0 equals 0 implies a1 equals 0. But because of that recursion that goes in 2 steps, automatically that means a3, a5, a7, all the odd coefficients will be 0. So that means the only eigenvalues will be the ones with an even, the only possible eigenvalues. That will give me non-zero solutions. So in that case, the lambda that you will take into account will be 2n, 2n plus 1. Again, because the standard way of writing an even number is 2n. So notice again, in both cases, lambda is of the form n times n plus 1, right? I mean a number times the next one. But with these extra boundary conditions, you either have an odd number or an even number. So that's why if you have an even number, you write it as 2n, so 2n, 2n plus 1. like this. And if it's an odd number, you'll have 2n plus 1, 2n plus 2. Okay, so now you may wonder, what about orthogonality on the interval 0, 1? Well, these functions remain orthogonal. Because remember, we just proved that no matter what m and n is, if they're distinct, this integral is still 0. So even if you take only the even or the odd one separately, this integral will still be 0. And you may wonder, how does that connect to interval 0, 1 as opposed to -1 and 1? Well, the problem is that if you take either the odd polynomials or even polynomials, the product of the two will be actually an even function. And the integral from -1 to 1 will be twice the integral from 0 to 1. And that allows you basically to find the other coefficients in that fashion. So let me just end up with this remark. And we'll continue next time on a different lecture with some other examples. So we know that if you have an even function, let's say you have a function g of x which is even. This is from calculus 2, for example, or calculus 1. If you take the integral of an even function on a symmetric interval, we know that's twice the integral from 0 to 1. So if I take the integral from -1 to 1 of g of x dx, if I know that g of x is an even function, then the integral from -1 to 1 is 2 times the integral from 0 to 1. We can see that from the graph, if you imagine how the graph looks like for an even function over a symmetric interval. So you can take just half of that integral. In our case, if I take even polynomials or odd polynomials at a time, the product of the two is still an even function. So let me just close it with this, and then we'll continue next time, because I don't want to make this lecture longer than it is already. So if I take p2n of x, p2m of x, so if I multiply two even polynomials, this will be an even function. But even if I multiply two odd polynomials, this is still an even function. Just like natural numbers. If you multiply two even numbers, you get an even number. If you multiply two odd numbers, you still get an even number. So the point I'm trying to make here basically is that when you take just even or odd polynomials at a time, you can still evaluate this very easily, right? I mean, the integral from -1 to 1 will be simply twice the integral from 0 to 1 of the same function. So it's just a matter of replacing n with either 2n or 2n plus 1, depending on whether you take the even or the odd cases. So all in all, and that's going to be the topic for the next week, we're going to deal essentially with three types of series involving the Legendre series. The one in which no extra conditions are assumed in the Sturm-Liouville problem, and that leads to Legendre series involving all Legendre polynomials, all of them, even and odd combined. And this will be the formula for the coefficients. Or you can have boundary conditions of this type, Dirichlet or Newman type. One of them leads to series in terms of the odd polynomials, kind of like sine series if you want, and the other one leading to even polynomials analogous to the cosine series. So next time we're gonna start, like I said, with a little bit more details on how you obtain these coefficients in the in the case of these boundary conditions. And after that, we're gonna make finally the connection back to the boundary value problem in spherical coordinates. And we're gonna finish up with examples. There is another, there are two more formulas to deal with, which will allow us to evaluate these integrals easily. I mean, easier than without them, but I'll talk about that in the next lecture. So I think that's it for today and for this week.